Hi, welcome back to my channel. My name is Gina. In this video, we're going to talk about derivative of trigonometric functions. So far, we've only looked at one derivative formula, the power rule. If you want to review that, I'll put the link up there. So in that video, we derive a pattern for a function of the form x to the power of r. But actually, we can use the definition of derivative function to find a pattern for other functions as well. So in this video, we're going to look at the trigonometric functions. So we will start with finding the derivative for sine of x. And before we jump into the proof, I want to introduce two special limits. The first one is limit of sine theta over theta as theta approaches 0. This limit equals to 1. But for now, we are not going to prove this limit. If you are interested in why, we need something called the Taylor expansions to prove this, and you'll only learn about the Taylor expansions in Calculus 3. So for now, we'll just take this result without proving it. And then the second special limit is limit of cosine of theta minus 1 over theta as theta approaches 0, and this limit equals to 0. Now let's prove the derivative for sine of x. So given f of x equals to sine of x, let's find the derivative of f of x. So we're going to start with the definition of derivative function, which is limit of f of x plus h minus f of x, the change in y, over h, the change in x. And we're going to take the limit as h approaches 0. So now let's substitute the function into the f of x plus h and f of x. So this equals limit as h approaches 0. F of x plus h is sine of x plus h minus f of x, which is sine of x, over h. Now we're going to expand the sine of x plus h using the trigonometric identity. So this equals to limit as h approaches 0. So sine of x plus h equals to sine of x times cosine of h plus sine of h times cosine of x. Then we continue with the equation minus sine of x over h. Now we're going to combine the first and the third term by factoring out the sine of x. So this equals to limit as h approaches 0 of sine of x times cosine of h minus 1 over h. Then the second term is cosine of x times sine of h over h. And since the limit is distributive, so we can distribute the limit to the first and the second term. So this equals to limit as h approaches 0 of sine of x times cosine of h minus 1 over h. Then plus limit as h approaches 0 of cosine of x times sine of h over h. And since sine of x and cosine of x, they are functions of x, but we are taking the limit as h approaches 0. So they are not a function of h, meaning that they are a constant in this limit. So we can take the constant outside of the limit. So this equals to sine of x times limit as h approaches 0 of cosine of h minus 1 over h. Then the second term, we can take the constant cosine of x outside of the limit. So cosine of x times limit as h approaches 0 of sine of h over h. Now we can use the special limits that I just introduced. So here we have limit of cosine of h minus 1 over h as h approaches 0. And that is the second special limit, and this limit equals to 0. Then we also have limit of sine of h over h as h approaches 0. And this is the first special limit, and this limit equals to 1. So in conclusion, derivative for sine of x is sine of x times 0 plus cosine of x times 1. So derivative of sine of x equals to cosine of x. Similarly, you can use the exact same techniques to find that the derivative for cosine of x equals to negative sine of x. And next, the tangent of x. So let f of x equals to tangent of x. And tangent of x also equals to sine of x over cosine of x. So to find its derivative, we can use the quotient rule, since we already knew the derivative of sine of x and derivative of cosine of x. So f prime equals to derivative of the numerator times the denominator, cosine of x, then minus the numerator, sine of x, times the derivative of the denominator, cosine of x, over the denominator square. And we just proven that derivative of sine of x is cosine of x. So we have cosine of x times cosine of x minus sine of x times derivative of cosine of x is negative sine of x over cosine of x squared, which equals to cosine of x squared plus sine of x squared over cosine of x squared. And cosine of x squared plus sine of x squared equals to 1. So this equals to 1 over cosine of x squared, which also equals to secant squared. So derivative of tangent of x is secant squared. Now let's find the derivative of cosecant, secant, and cotangent. So cosecant of x equals to 1 over sine of x, and we can rewrite that as sine of x to the power of negative 1. And similarly with secant of x and cotangent of x, secant of x equals to 1 over cosine of x, and cotangent of x equals to 1 over tangent of x. So now we can use the chain rule version of the power rule to find these three functions. For example, the first one, y prime equals to negative 1 times sine of x, the inside function, to the power of negative 1 minus 1, which is negative 2. Then times the derivative of the inside function, and derivative of sine of x is cosine of x. So here we get negative 1 over sine of x times cosine of x over sine of x. So the first term, 1 over sine of x equals to cosecant of x. And this equals to 1 over tangent of x, which also equals to cotangent of x. So in summary, derivative of cosecant of x equals to negative cosecant of x times cotangent of x. And you can use the same trick to find derivative of secant of x is secant of x times tangent of x. And the derivative of cotangent of x is negative cosecant of x squared. A quick summary of all the derivative functions we learned in this video. So first, we've proven the derivative of sine of x, which equals to cosine of x, using the two special limits. And we can use the same techniques to find the derivative of cosine of x, which is negative sine of x. Then we use the trigonometric identity, tangent of x equals to sine of x over cosine of x, and then we use the quotient rule to find that the derivative of tangent of x is secant of x squared. Then we use the chain rule version of the power rule to find the derivative of cosecant of x, secant of x, and cotangent of x. Now let's look at some examples. The first one, sine of x times tangent of x. So y is a function of x times another function of x. So here we need to use the product rule. So y prime equals to derivative of the first function, and derivative of sine of x is cosine of x, then times the second function, tangent of x, then plus the first function, sine of x, times the derivative of tangent of x, which is secant of x squared. Now let's look at the second example. Y equals to x squared times secant of x. So here again we have a function of x times secant of x, which is another function of x. So y prime equals to the derivative of the first function times the second function, secant of x, then plus the first function, x squared, times derivative of secant of x, which is secant of x times tangent of x. Now we're going to look at the chain rule version of the derivative of trigonometric functions. So a quick recap, if y is a composition function, f of g of x, then derivative of y is derivative of f, and the input is still g of x, times derivative of g of x, the inside function. So for example, if y equals to sine of an inside function, then derivative of y is cosine of the inside function times derivative of the inside function. For example, y equals to sine of x squared. So the inside function is the x squared. So y prime equals to cosine of the inside function, x squared, times derivative of x squared, which is 2x. Now let's look at the second example. Y equals to tangent of cosine of x times cotangent of 2x cubed. So here we have a function of x times another function of x. So here we need to use the product rule. So y prime equals to derivative of the first function times the second function, cotangent of 2x cubed, plus the first function, tangent of cosine of x, times the derivative of cotangent of 2x cubed. Here we have tangent of an inside function. So here we have to use the chain rule. So derivative of tangent is secant squared. So this equals to secant squared of the inside function, cosine of x, then times the derivative of cosine of x, which is negative sine of x. Then we continue the equation times cotangent of 2x cubed plus tangent of cosine of x times derivative of cotangent of an inside function, 2x cubed. And the derivative of cotangent is negative cosecant x squared. But here instead of x, we have the inside function, 2x cubed. Then times the derivative of 2x cubed, which is 6x squared. And that is the end of the video. If you have any questions, feel free to comment below, and I'll see you in the next video.